In number 15, we are going to find the z-score that corresponds to a specified area or probability. In section 5.3, there's a visual picture that represents what we're doing. We have an area given to us, like one of these shaded in blue parts of the graph, and we're going to try to find the z-score that corresponds to that area. In Excel, to solve this, you'll use the formula norm.s.inv, and then you enter that area that you're looking for. And here I've entered it, and Excel will give back the z-score that corresponds to that area. 16 is similar to 15. We're trying to find the z-score that corresponds to a specified area. In Excel, use the formula equals norm.s.inv, type in that cumulative area, and Excel will give you back the z-score. Number 17, we're trying to find the z-score that corresponds to a given percentile. So we're looking for the 20th percentile. In other words, 20% of the normal distribution would be to the left of the z-score. And so it's like a picture like this where we have 20% of the normal distribution shaded in, and we're looking for the z-score that shows the 20% cutoff mark. 20% is the same as 20% of the area, so we're using that same formula here, norm.s.inv, and we just want to put 0.2 in there for 20% of the area, or the 20th percentile being to the left of this particular z-score. In 18, we're finding a z-score that corresponds to a given percentile. This is just like 17. Here we're looking for the 97th percentile. So we want the z-score where 97% of the distribution is to the left of that z-score. So equals norm.s.inv and type in 0.97 and you'll get the corresponding z-score. 19 is similar to the previous problems, but we have a picture here. It's showing us that the area shaded in of our normal distribution is 0.3745, and we want to find the z-score corresponding to that amount of area to the left of the given z-score. In Excel, equals norm.s.inv, type in the amount of area we're looking for, and you'll get the corresponding z-score. In number 20, we're trying to find here the z-score that has 0.0475 to the right of it. And there's two ways we can approach this. We can do norm.s.inv with that area value in there, and it gives us back negative 1.67. Excel always gives back left-hand calculations, so that negative 1.67 is a z-score over here, and there's 0.0475 in the left-hand tail. But by symmetry, we know the normal distribution is symmetric on either side. And so if negative 1.67 has this amount of area to the left, then positive 1.67 has that amount of area to the right. So by symmetry, you can just switch that answer from the negative to the positive. Or you can think of it this way. We're looking for 0.0475 to the right. So how much would we be looking for to the left? Well, 1 minus 0.0475 gives us that result. So equals norm.s.inv, type in that result. Then we get the z-score that would have that much to the left. And that's the same z-score that would have the amount we're looking for to the right. 21, a similar problem to what we've been doing, just worded a little different. Looking for a z-score that has 10.2% of the distribution's area to its left. We just need to change that percentage to a decimal. 10.2% as a decimal, and equals norm.s.inv. Excel will give back the z-score that has the given percentage to the left. 22, we're going to find the z-scores for which 20% of the distribution lies between negative z and positive z. So our answers are going to be two z-scores that have the same exact numbers, but one's positive and one's negative. A good way to solve this one is to use the symmetry of the normal distribution. If we have 20% between our two z-scores, that means 80% would be outside of those two z-scores. And so by symmetry, there would have to be 40% on either side of our two boundaries. This is a good illustration, even though the numbers are different than the problem I'm working on. It just illustrates how that part outside of each of our boundaries here would be symmetric on either side of our normal distribution. So if we know we need 40% on the sides, we can use this formula, equals norm.s.inv with a 0.4, and it gives us one of the z-scores, and the other one would be the positive with the same numbers. In number 23, we have data that has a normal distribution. We're given the mean and the standard deviation. And the first question is to find the value that represents the 95th percentile. In Excel, we want to use norm.inv, no s, just norm.inv, and then you enter the area you're looking for. In this case, the 95th percentile would be 0.95. And then the mean of your distribution and the standard deviation. Excel will give back the value that represents the 95th percentile. The second part of the question is about finding the value that represents the first quartile, and the first quartile would be the 25%. So using that same formula in Excel, we want to enter in 0.25 to find the value that represents 25% of the data would be to its left, the first quartile. Number 24 is all about the central limit theorem. And the central limit theorem and sampling distributions, you can read more about them in section 5.4. Basically, with a sampling distribution, we're looking at all the samples of the same exact size. And if we were to look at means of all those samples of the same size, then we would have the sampling distribution of all those sample means. And that's what we're doing here in this problem. Our population is only 3 data values, 98, 95, and 94 in this example. So first, let's find the mean of our entire population and the standard deviation of our entire population. So with these data values, if we do equals average of them, we get the population mean, and we need to do the population standard deviation, so equals stdev.p for population, and we get the population standard deviation. And now we're going to look at the sampling distribution of the sample means for samples of size 3. So we want to think of every possible sample we could get of size 3 if this was our population data. And notice it says we're drawing with replacement, so you select a number from these 3, and then you can select the same number again for your second and for your third choice. So to quickly think of how many total samples there would be of size 3, there's 3 numbers to pick from for your first value in your sample. And since we're doing a replacement, there's still 3 for your second value, and there's still 3 numbers for your third value in your sample. So there's 27 total different samples. And for each of the different samples, we want to find the mean of that sample. And so all these different means is what we're looking at when we talk about the sampling distribution of the sample means. These are all the possible sampling means. We want to see how they are distributed. And so I've actually listed the 27 different means from our 27 different samples over here in Excel. And if you want to find the mean of all those different sample means, you take the average of them. And notice that this value, it's exactly the same as the mean from our population. And that's always going to be the case for the sampling distribution. It's going to have the same exact mean as the population mean. And that kind of should make sense. Some samples are going to have a mean that's a little bit less than the population mean. Some will have a mean that's a little bit more. Some will be right on, have the exact same mean as the population mean. And when you average all of that out, you're going to get right to the population mean. Now let's look at the population standard deviation, and let's compare that to our sampling distribution standard deviation. So here, standard deviation dot p, because I have the means here for every single possible sample. I have the whole entire population of samples. I want to use dot p. So select that data, This would be the standard deviation of all those different means from our samples of size 3. So 0.98. And that is definitely smaller than the population standard deviation. And again, this will always be the case because with your samples, your sample means tend to not be as varied as all the actual data because really low values in the sample balance out with really high values in the sample. So the sample means all tend to hover a lot closer to the population mean than the original data hovers to the population mean. So we're going to have a smaller standard deviation always with our sampling distribution. On page 263, it starts talking about the central limit theorem, and I wanted to point out this study tip here. The distribution of sample means always has the same mean as the population, and its standard deviation is always less than the standard deviation of the population. So the sampling distribution has the same center as our original population, but it is not as spread out. And another great point in this study tip here is that if you can look at larger and larger sample sizes, so we just looked at samples of size 3, but if you looked at samples of size 30, let's say, the sampling distribution gets less and less spread out the larger the sample size gets. The sample means will be even closer and closer to the population mean. And the last part of this problem is just what I've been talking about, comparing the population and sampling distribution. They will have the same means, but the standard deviation of the sampling distribution will always be smaller.